All right, so like I said, I'm going to try to free up more class time for practice problems, but the flip side of that means I will ask you guys to do some studying at home, primarily naming. Naming, in my opinion, is really easy. You can read section 14.2 in your book, but naming ethers is really straightforward, and we'll actually go through a couple practice problems too, so you can get a rough idea. But let's take a look at some common ethers. There's a handful of ethers we see all the time in a lab setting, the most common of which is diethyl ether. It's pretty easy to name, right? It's an ether with two ethyl groups coming off of it. Alternatively, what you can do is find the longest carbon chain that contains your ether functionality. In this case, it doesn't matter which one you choose. So for example, I'd say, all right, this is a 1,2 carbon chain. We've got an ether group coming off of carbon 1. So alternatively, you could say this is ethoxyethane. However, nobody calls it ethoxyethane. It's a heck of a lot easier to just call this diethyl ether. But anytime you're looking at an ether substituent, you would just call it whatever it is with an oxy substituent, and you put that in the front. So for example, you might see methoxy, ethoxy, propoxy, things like that. Those are treated as substituents coming off of some longer carbon chain. All right, so that's a really common ether. Where have we seen this used? Both in lecture and lab. You guys remember when we used it in lab? We did the extraction stuff, right? So this stuff stinks really bad. It's quite flammable, but it's a really, really good organic solvent, and it's easy to boil off or evaporate. So it's commonly used in extractions. It was also used in our Grignard reactions. You guys remember that? It was a solvent that we used for a lot of our Grignard reactions, and we'll talk more about that later, but it actually helps with Grignard reactions. The next one that we've seen a lot of too is this one called Petra hydrofuran, also known as THF. Where have we seen this?
BH3-THF?
Yeah, BH3-THF. If you remember, I said that boranes are incredibly reactive, and so they tend to coordinate with ethers to make them more stable. So that's a really common one. Another common one that we really haven't seen much of, but is fairly common in organic labs, is this one. It's called 1,4-dioxane. Really, the benefit of using 1,4-dioxane is it's an ether, but it has a much, much higher boiling point than diethyl ether, and so you can crank up the heat and drive your reactions to completion a little bit easier. THF is kind of in the middle, so it's in between in terms of its boiling points. All right, so let's take a look at why we use ethers. All right, there's a few common ones I've mentioned already. It's a common solvent. We saw that in our extraction lab during first term. We've seen it with Grignard reagents in lecture. The other thing I mentioned is it can be a Lewis, actually I'm going to put weak Lewis base. What does it mean when you're a Lewis base? Doesn't have to do with protons. It donates electrons, right? So if you think about it, we said borane. If you look at it, is this trigonal planar compound. We said that it's really, really unstable. You can't just buy a bottle of borane. And that's because it's got this empty p orbital, pretty unhappy. And so what happens is, for example, when it's in THF, we said that this lone pair is going to dump into that empty p orbital and actually form a Lewis acid-base adduct. Where you essentially form a new bridge. This oxygen carries a positive charge and the boron carries a negative charge. So that's what BH3-THF looks like, is it's basically just tethered up borane. All right, the reason we like using this as a solvent is it's fairly inert. What does it mean when I say inert? Yeah, non-reactive. Most of the time, your solvents that you use in organic chemistry, you don't want to do anything besides just be a medium for the reaction, right? There are some examples outside of that, but this is a pretty good solvent. Depending on which one you use, it can be classified as nonpolar, as in the case of diethyl ether, that's relatively nonpolar, or polar, as in the case with THF. So it's got a wide range of polarity, too. The other thing, too, is it's got a good H-bond acceptor. So you may occasionally see this. So let's say you've got this generic ether, and then you've got some sort of hydrogen bond donor nearby. In this case, I'll have an alcohol. This interaction here is actually highly stabilizing, so that lone pair on ether can essentially help coordinate a hydrogen bond. So it's not the greatest hydrogen bond donating system, but it's pretty dang good. Does that make sense? A little bit of review from first term. Yeah. All right. That leads me to the next one. I really like this graphic. This gets into a unique type of ethers called epoxides. And what a lot of people call these is the black sheep of the ether family. So you can see this kid clearly doesn't fit in with his family, doesn't look super happy. And so let's take a look at generic epoxides. And we'll try to understand why they're the black sheep of the ether family. Whoops. Let's say I want to make this epoxide. This is commonly known as ethylene oxide. And why is it called ethylene? Does anybody remember that from our previous lecture? Yeah, there's two CH2 spacers, right? So this is ethylene oxide because of those spacers, not because there's a double bond. How do we go about making an alkene into an epoxide? What reagent do we need? MCPBA, the metachloroperoxybenzoic acid. It's the one we're most familiar with, right? And then if we throw in acid and water, we can make a diol. But we can stop here and actually just work with this epoxide. Why is this so different than normal ethers? It's a triangle? That's one reason. What about being a triangle, though? Why are triangles? Oh, yeah, exactly. So let's make some notes. It's very reactive. Due to ring strain. So if we look at it, each of these carbons right here, what's the hybridization? There's sp3, right? They've got 4 bonds to them. So steric number of 4 means it's got to be sp3. All right, sp3 normally wants what bond angles? 109.5. In this case, we're pushing them into about 60-degree bond angles. Super duper unhappy being that way. That's why these are very, very different. If we look up here, I said ethers are fairly inert or non-reactive. This is clearly the exception to that rule, right? They are not happy because we're pushing them into this ring system way outside of their Vesper angles. All right, so this is one type of cyclic ether. I did want to show you a few others. However, they're a lot less common. All right, the first one is a 4-membered ring with oxygen in it. These are called Occitanes. The next one looks like THF, but as a generic functional group where you've got an oxygen in a 5-membered ring system. These are called oxolanes. Whoops. And there's quite a few others. I'm not going to be super picky about these. Really, the one I want to focus on primarily in this chapter is going to be the epoxides. The epoxides are really versatile building blocks in the polymer industry and in organic synthesis, so we're going to be looking at these a lot. These are a little bit less common. In fact, I said oxalanes like THF are common solvents because they are inert. They don't do very much in terms of reactivity. Make sense? All right. I did want to talk about a side topic simply because I can. And these are crown ethers. These are really unique ethers. I'm not going to get super into this, but I do like the chemistry involved in it because it's what I spent a lot of my PhD working on. And crown ethers are very unique. If you look at this one, it's got 4 oxygens in a ring system. And this is called 12 crown 4. And why do you think it's called 12 crown 4? Yep, it's a 12-membered ring system with 4 oxygens evenly spaced throughout it, right? So 12 crown 4 is pretty famous. There's another one too with 1 more oxygen on it. So I'll just draw all my oxygens, and then it's got all these ethylene spacers. And this is called 15 crown 5. And then last but not least, we've got the biggest of them all, at least the most common one. Whoops, sorry. Let me space this out differently. This one has 6 oxygens in it. And what do you think this one might be called? 18 crown 6. The goofy thing about these is that they really, really like to lasso cations. So if we look at these, we could say, all right, lithium is one of the smallest cations that we have. It likes to just sit in this pocket right here. So lithium gets tied up. Sodium, on the other hand, if we look at the periodic table, is a little bit bigger. Sodium doesn't fit in that pocket really well. Where do you think sodium would fit in well? 15 crown 5. So sodium in this case just sits in this pocket, coordinates with all these oxygens. This lasso is a little bit too big for lithium and a little bit too small for potassium, but we know potassium can likely fit in the next biggest one. And so you might be wondering, why do we care about these? Who cares about binding cations and anions? And that brings me to this next point, that these mimic a lot of biological systems. So if we look at this compound right here, essentially you can see a similar pattern of oxygens pointing inwards in a ring system. And in fact, this is roughly the same size as 18 crown 6. Potassium just sits in here, and the oxygens like to essentially donate lone pairs to that potassium cation. This drug is called vanillamycin, or VANILOMYCIN, and it binds potassium 1,000,000 times stronger than sodium. That makes this an incredibly powerful antimicrobial drug because it will disrupt a lot of the cell regulation by basically wrapping up all of the available potassium. So a lot of these drugs are basically similar to these model systems that we have made. And this type of chemistry is called host-guest chemistry, where we purposely try to design molecules that will capture or encapsulate other molecules. And we do that oftentimes to study how our body works, right? If you think about biochemistry or molecular biology and enzyme reactions, right? Enzymes have that lock and key fit. We're still at this elementary stage of making crown ethers and studying how they behave. However, as we get further along, they're getting more and more complicated to the point where we're actually able to make little molecular machines now. I'm not going to spend too much time talking about this, but it's one of my favorite areas of chemistry because it's this crossover between chemistry and biology. One cool reaction that you can do with this, I did want to show you. So let's say I take potassium fluoride. A lot of first-term students will say, well, can't we just do SN2 chemistry and swap off that bromine for fluorine? The reality is this reaction will not work. And it gets a little bit complicated, but this has more to do with the electrostatic pairing between the potassium cation and the fluoride anion. They just hold on to each other so tightly that fluoride never even has a chance to do SN2 chemistry. So they call this tight ion pairing. All right, so as a chemist, what do you think a solution could be if you just absolutely need to get this fluorinated product? Yeah, you could still use potassium fluoride, but what could you use to maybe break up that ion pairing? 18 crown 6. So this is commonly what these crown ethers are used for, is they're used to break up ion pairing to make your anion that much more reactive as a nucleophile, base, etc. So this is a more modern branch of chemistry, and the Nobel Prize was awarded in the 60s for the chemists that helped develop this. All right, I know it's kind of an offshoot, but interesting stuff. Let's talk about, what's that?
It's on sapling.
It's on sapling too?
Yeah, there was like 2 questions.
That's good then. All right. Let's take a look at the industrial preparation of ethers. And then we'll get into more complicated ones later. Whoop. Really, this method's only used for the most simple ethers. So only used for simple / small ethers. But what you can do is start out with ethanol. You can treat it with strong acid, and we know acid-base chemistry is the fastest reaction, so this ethanol will quickly get protonated. And what do you think happens if you've got another equivalent of ethanol around?
Give me an attack.
Give you a hint, this is a poor leaving group. This is a good leaving group. That means our alcohol can probably do an SN2 style attack. Kick off this leaving group. It gives us this. We know water got kicked off as a leaving group. And then what do you think happens in the last step to give us our final ether? Yeah, deprotonation. And we know this can occur pretty rapidly because we've got water around. So when you do this, you can make diethyl ether. It's one of the common ethers, and you regenerate your acid. So this is a catalytic system. And you can use this to make pretty small ethers. The problem is this requires really strong acid and usually fairly high temperatures. So it's not the best reaction to do if you've got a precious natural product that could degrade easily. This is only used in really simple, easy cases. We have seen other ways of making ethers, and I'll show you guys a little bit of that. However, we didn't really talk about the naming before. This is called the Williamson ether synthesis. And again, this is just a fancy name for SN2. I wish I could get a reaction named after me for something this simple.
Scientists are pretty vain.
Yeah. The funniest thing about that, though, is this is completely unrelated. Scientists sometimes try to push it, and they're like, I'm going to name this reaction after me, and then they publish it, naming it after themselves. Nobody will call it that name. It only works if you don't try to make it happen. It's this weird thing among the community. All right, so first thing we need to do is we know here this is a poor nucleophile. So what do you think we could do to turn this into a better nucleophile to do SN2 chemistry? Tosylating it would change it from a poor leaving group to a good leaving group, but we want it to be a nucleophile.
So maybe
Deprotonate it, right? So the whole idea here is we can convert this to an oxygen with a negative charge. What's this called? It's an alkoxide. Do you guys remember that? So we can convert this to an alkoxide. All of a sudden, this is a good nucleophile because that oxygen's got a negative charge. What reagent should we use? We saw this last term, or last chapter.
Metal.
Yeah, we can use a metal, right? So for example, we could use something like sodium metal. That means our countercation would be Na+, and we generate half an equivalent of hydrogen gas as our byproduct, right? Pretty easy to do. The key with the Williamson ether synthesis is you first need to make an alkoxide by treating it with an alkali metal like sodium, lithium, potassium, and then you treat it with your electrophile. So step 2, we need some sort of electrophile. So for example, maybe I've got some sort of halogen hanging off here. So this would be a good leaving group. Maybe bromine, something like that. During this step, we can now do SN2 chemistry, kick off our leaving group. And I'm going to make this R prime on that side. So now we can see we've made our own ether, and then our byproduct for this reaction is going to be NaX. That's our sodium spectator cation and our leaving group that got kicked off. So this is a really simple way to make ethers, especially more complicated non-symmetric ethers. If we look at the above reaction up here, this really only works for making symmetric ethers. You have zero control if you want one side of it to be different from the other side. But by using this method, all of a sudden we can control whether or not we want 2 carbons on one side and 5 on the other, or some variation thereof. Does that make sense?
I know this may be a bit unrelated, but could R be like some carbon group or hydrogen or something like that?
R could be any carbon chain. R is just a placeholder for some carbon group, right? The other important thing to remember too for SN2 is that this carbon right here needs to be methyl or primary. Why don't we do secondary or tertiary? It would favor E2, right? Our alkoxide that we made is also a good base. We don't want E2 reactions. We only want SN2 reactions. So we do have to be careful with the electrophile that we use. All right, tomorrow when we come in, we'll talk about some other reactions. Or Wednesday when we come in, we'll talk about reactions of ethers and continue on talking about epoxides.